Welcome to ACS Webinars, bringing you the best and brightest minds in chemistry, live every Thursday at 2 p.m. Eastern. To view our upcoming schedule, please visit acs.org/acswebinars.
I'm Joseph Fortunac. I'm here with Professors Anthony Rappé and Brian Laird, respectively from Colorado State University and from the University of Kansas. The title of this afternoon's presentations is overarching the idea of catalyzing innovation through molecular design. So understanding and predicting the macroscopic behavior of materials in terms of their microscopic and their molecular interactions is really at the forefront on the fundamentals of real scientific endeavor. So the difference, though, between various scientific disciplines is between chemistry, physics, biology, material science really begin to disappear as traditional macroscopic phenomenology is replaced by a more molecular approach. And I'm paraphrasing a lot of quotes from Brian Laird when I say that. Now, let me introduce this afternoon's presenters. Anthony Rappé is a director of the C-Clear Catalysis Collaboratory for light-activated earth-abundant reagents. The Rappé research group uses molecular mechanics and ab initio electronic structure techniques to study novel catalytic reactions. So these include olefin polymerization and the selective oxidation of methane and of olefins. Now, the Vision 2020 Catalysis report cites both polymerization and the oxidation of methanol and olefins as critical fields for the future development of new sustainable chemistry. Brian Laird is a professor and chair, and he's going to speak about sustainable chemical innovations by an integrated design approach at the Center for Environmentally Beneficial Catalysis, where he's the principal investigator on a collaborative grant. Professor Laird's research specializes in computational material science and applied statistical mechanics. Three areas of particular emphasis for his research work are crystal melt interfaces of complex systems, fundamental investigations into gas-expanded solvent media for green chemistry, and algorithms for molecular modeling. And now I'll turn the floor over to Professor Rappé.
Let me begin by thanking the ACS for the opportunity and participating in this webinar, this description of catalysis research across a wide range. I'm going to be describing work that is funded by the EPA and NSF. It's a collaborative project involving 5 co-PIs, where what we're interested in doing is developing catalytic processes that use sunlight and earth-abundant materials to develop new pharmaceutical reagents. And so a major goal is obtaining enantioselectivity. A second major goal is being able to activate CH bonds. This effort includes coordination chemistry. Matt Shores is a coordination chemist, a magnetochemist, and as we'll see as we understanding electron spin is an important part of our thesis. Niels Damrauer down at Boulder uses transient absorption spectroscopy, be able to ultra-fast kinetic processes, look at excited states of molecules on a rapid timescale. My group does theory on these catalytic processes to try to understand, and sort of the closers in this effort, the people that actually produce the bottom line are Eric Ferrar and Tom Rovis's group that develop synthetic organic reagents predominantly for the pharmaceutical industry. To get started, I want to talk a tiny bit about sustainability, what we mean by sustainability. These are sort of two, I wouldn't say orthogonal, but certainly different descriptions of sustainability. One is sort of this triple bottom line analysis that people use to think about the global economy, the environment, and society, with a fourth dimension of needing to understand what's going on and be able to explain to people what's going on. An alternative way of thinking about sustainability is connections between life, water, food, and energy, all of these things which are interconnected, all of these things which really involve chemistry. As we go through, see that I'm quite interested in visual representations of things. People remember visual things quite well. In this particular diagram, which is the per capita energy use as a function of Human Development Index, we can see that the challenge ahead, really, bottom line challenge ahead, is figuring out how to bring us back in terms of our energy use without impacting the Human Development Index, while bringing up the developing world. That's a big part of the challenge is, for example, figuring out how to do catalysis with inexpensive reagents. So 12 principles of green chemistry sort of flow through what we're going to be talking about. This nice little book reference down here at the bottom, inexpensive, but does summarize things fairly well in terms of describing what's going on. We're going to be focusing in on not all of these principles, but using a number of them. To get started on things, scale is always a big factor. How big is this? How big is the endeavor that we're looking at? Annual petroleum, U.S. petroleum production, about 1 billion metric tons produced a year. About 15% of that is used in the petrochemical industry. Petrochemical industry is the area that Professor Laird is going to be talking about a little later. Less than 0.1% of the materials, the chemicals produced, is in the pharmaceutical industry. And so on a global scale, it's really a small number, a small amount of material. If you can compare food consumption, we actually deal with more metric tons of petroleum a year than we do food. Natural gas, about half as much in terms of consumption. 30% of that for chemicals, roughly half of that producing fertilizer. Revenue, chemical shipments, $5.2 trillion a year chemical shipments. Pharmaceutical industry, about $1 trillion. If you take these numbers and compare them to these numbers, drugs are a fairly high valued product. If we compare that to energy, chemical shipments are a more valuable commodity than energy. So the pharmaceutical industry may be a small volume contributor, but is certainly a high value part of the chemical landscape. Key point that is going to run through what I'm talking about. I'm going to go through several sort of background introductory aspects before describing the research, but selectivity is really central to the underlying 12 principles of green chemistry. Waste energy reduction, key attribute. Catalysis can play an important role by, instead of using stoichiometric reagents, you can use sub-stoichiometric reagents. You can lower the energy of the process, saving energy. Improved selectivity, that ties into atom economy, reducing the use of auxiliary agents. We'll see that's one of the things we've been able to accomplish. Product control, reducing side products. And something that doesn't tend to get discussed a lot in this context is stereo control. Stereo control. You want to make one enantiomer, typically, and we'll talk about that next slide or two. Making one enantiomer, you cut the waste down in half. Okay? You can improve the product safety because fairly often the wrong enantiomer is not necessarily a safe process, and you can increase your understanding of pharmacodynamics by having stereo control. So what is stereo control? What do we mean by stereo selectivity? I'm showing here the two enantiomers of ketamine. There is effectively a mirror plane. You can think about them as right and left hands in terms of they are mirror images, but they're not superimposable. Generally speaking, stereoisomers have different biological activity. just like you can't put your right hand in your left glove very easily. The most benign option is that you end up with 50% waste if you make both. Alternatively, one of the isomer could be active and the other could have a negative side effect. Or the isomers could have opposite effects. That clouds drug discovery in terms of what is the actual drug profile for a substance. Ketamine. Ketamine is an anesthetic agent. It also induces psychedelic hallucinations. It is a drug of abuse in terms of a club drug, but it has some very interesting attributes, and it actually is being tested these days as an antidepressant, and it also is being used as an anti-suicide agent. It can, if you will, quench suicidal thoughts relatively quickly. So the S enantiomer is associated with the analgesic properties, whereas the R enantiomer is associated with the hallucinogenic properties. Wouldn't it be great if you only had one without the other? But commercially available ketamine is actually the racemate. It has both stereoisomers in it. If you look at the active site for ketamine bound into an inyl channel called GLIC, this is one of the enantiomers in the active site. You can see stabilizing interactions, and it turns out this is the R enantiomer of ketamine in this active site. The other glove, the other hand, doesn't fit. The shape actually makes a difference. Another drug, an opioid analgesic, one enantiomer is agonist, the other an antagonist. The racemate is a weak agonist. So sorting out the impact requires being able to control the stereochemistry. So we have stereochemistry catalysis. What is catalysis? Well, this is one example of a catalyst. If you take cyclohexadiene, heat it up in a sealed tube greater than 100 degrees, you end up making a product. Relatively large activation energy. If you add a catalyst, you change the reaction pathway and the activation energy drops dramatically. Instead of needing over 100 degrees, the reaction can occur at 0 degrees, and in fact, heating it up decreases the effectiveness of the reaction. So a catalyst adds steps, but allows the reaction to occur at lower temperature. And lowering temperature allows you to increase selectivity. This is a graph of selectivity as a function of energy difference and as a function of temperature. And so if you decrease the temperature, your selectivity increases. And so important attribute in thinking about what we're trying to do is how do you increase selectivity and lower the temperature for the reaction? So one way of doing that, a way that we're involved with exploring, is through what's called photoredox catalysis. You take a metal complex, a dye, you excite it, you have an auxiliary agent that's either reduced or oxidized. That generates a oxidized or reduced metal complex that can then can go on to do chemistry. And as we'll see, compared to photovoltaics plus electrochemistry, you can often get increased selectivity by doing photocatalysis. Abundance, earth-abundant materials. If this is a periodic table, three-dimensional periodic table, where what's plotted is millimoles per mole. So millimoles of a substance per mole of earth. And iron is up here in terms of the scale. Iron, titanium, very earth-abundant materials. They're not as abundant as, say, silicon and oxygen, but they're quite a bit more abundant than a number of elements, other elements in the periodic table. So if you're thinking about doing something inexpensively, having an inexpensive metal would be quite desirable. Compared to second and third row elements, compared to the more traditional catalysts, they're more abundant, they're more reactive. They tend to undergo one electron processes. and they are spin active. They interact with magnetic fields. These are challenges, but they can be an advantage. If you can control them, having a more reactive species, you can carry out the reaction at lower temperature. You can use the spin attributes, and you can involve the ligands in redox events. And down here at the bottom, indicating several review articles that talk about this area. Stereo control is quite recently being added to photoredox chemistry, typically through a tandem process where you have the photoredox event coupled with an activation by a chiral Lewis acid, though quite recently Magers has come up with an iridium catalyst that carries out both of these activities at one metal center. So part of what we're about in terms of this webinar is combining models in terms of innovation using molecular design. And a big part of molecular design is coming up with visual images or coming up with ways of thinking about reaction. And one of the goals is to come up with safer chemical processes. And rather than needing to go look up in some table the toxicity associated with a specific compound, coming up with ideas to how to think about things in general is important. And so triphenyl hydride, which is shown in this active site of a transcription factor, binds to things like estrogen receptor sites. And the key part of this is that a lot of this molecule is hydrophobic. A lot of this molecule is hydrophobic. This isn't flat. This isn't flat. This can fit into the active site of this molecule. So triphenyl hydride can bind to a estrogen receptor site and cause deleterious action. So electronic structure theory is one of the tools that we use in our molecular design effort. Basic pathway is we start off with an experimental understanding, an observation, develop a theoretical model for that. This is self-calibrating in that if you don't reproduce the experiment, there's no point in going further. And then the theoretical model can be used to suggest additional experiments which can be carried out, and you either confirm the model or find out that something's going wrong. And so this is an internally calibrating process to combine theory in with experiment. So theory versus experiment. What I'm showing here, we're thinking about electronic spectroscopy. We're thinking about screening large numbers of ligands to find out what ligands we should use. And we can, and this figure compares theory and experiment, and you can see that the agreement is only qualitative, but it is qualitative, and one can use it to look at a series of metal complexes and a series of ligands, a series of metals, and come up with some general statements that, for example, zinc is probably too short of wavelength, too high of energy. Vanadium has greater intensity than chromium, and that one particular ligand looks most promising for use in catalysis. So now looking at some selectivity. This reaction, which I talked about earlier, this dimerization of cyclohexadiene, if you carry out this reaction electrochemically, what you found and what people found a number of years ago was you make polymer. You don't do the Diels-Alder reaction. The overpotential needed for the chemistry is such that you don't make the right product. If you use a chemical oxidant, you can achieve stereo control product, a reasonable product distribution. An interesting factor here is that the reaction as drawn is actually uphill, but it happens. It's an interesting question. Why? And it happens at low temperature and not high temperature, but it's uphill. The proposed mechanism involves taking an electron off of the diene, generating a radical cation species. Radical cation species can react with another equivalent, making this radical cation, which can lose the electron to cyclohexadiene again and undergo a radical chain process to make product. And so the initiation step may well be uphill, but the overall reaction can be downhill. Looking at this reaction computationally, what you find is that this first initiation step that's uphill, the electron transfer event, and so the bottom blue pictures are showing the path of the electron. What happens to the electron as the unpaired electron is a function of reaction. The reaction enthalpy is going downhill. You're binding the cyclohexadiene. This is going downhill, but the top is showing red is negative charge, blue is positive charge. The transition state, before the transition state, the electron transfer event hasn't occurred, but at the transition state, the electron transfer event is occurring. And so it isn't, if you will, what's a classical outer sphere reaction. It's more of an inner sphere coupled electron bond forming process. So another example of a diene-ene type reaction, which has been done with photocatalysis, react isoprene with an anethol. You can make with a ruthenium catalyst. You can make good yield and high diastereoselectivity. This is work out of the Yoon labs. You can also, but coupled, there's this methyl biologen auxiliary agent that's there in stoichiometric quantity. Methyl biologen, you may remember, is paraquat. Paraquat is somewhat toxic. It's a herbicide, probably not the best thing to have around. They can get rid of that by increasing the oxidation potential of the metal species, but oxygen is a stoichiometric reagent in this case. So reminding you that in general for these outer sphere processes, you have an auxiliary agent. Now that's okay in the pharmaceutical industry where you have small quantities, but if you're thinking about making gasoline, having a stoichiometric side reaction, probably not what you'd like. And so it'd be good to be able to get rid of this auxiliary agent. This auxiliary agent is there because of the lifetime of the excited state. We're doing chemistry in the excited state. The chemistry has to happen faster than the excited state decay. Ruthenium has a lifetime of roughly 600 nanoseconds for the bipyridyl complex. Chromium, on the other hand, is 69,000, quite a bit longer lifetime. And so can you use chromium instead, exploit the lifetime of chromium to carry out the chemistry without an auxiliary agent? The excited state is of chromium is this spin-flipped excited state, spin forbidden, can't go back to the ground state easily, sticks around a long time. This would be a description that you'd see for this excited state in inorganic chemistry. It's actually quite a bit more complicated than that. It isn't just this picture. It's this picture minus this picture minus this picture. This has a significant impact on the energetics, and that makes the modeling significantly more challenging. Okay, so the questions for C-Clear then are, can you use a first row transition metal? Can you exploit this lifetime to eliminate the auxiliary agent? Can you get stereo control for this radical process? And can you get reactivity that's not typically observed? Can you get novelty? Can you do something different? If it's just going to be a plug-and-play replacement, it's not going to be as exciting as if you can get novel chemistry. So, catalyst synthesis is involved in the process. Photo catalyst screening is involved in the process. Laser spectroscopy, now this isn't out of Star Wars, those actually are to protect people's eyes. And in terms of the time-resolved spectroscopy, we can see that our photocatalyst plus the reagent the reagent actually quenches the excited state. And so there's competition between reaction, productive reaction, and not productive reaction. And this time-resolved spectroscopy can play an important role in understanding. High-throughput screening, carrying out a number of experiments in parallel, have a grid of solvent and catalyst conditions. The goal here is to utilize this excited state to carry out CH bond activation. In that previous experiment, no dots, nothing worked. The excited state is formed, but the reaction is quenched by the molecule. Here, we are seeing some activity, some productive results through this rapid screening process. Theories combined into the process, so chromium, getting to sort of the heart of the story. Chromium-3 absorbs visible light. It does have this long-lived excited state, and this long-lived excited state has a very large oxidation potential. It is a very strong oxidizing agent. Does it work? Well, yes, it is productive. This model reaction of dicyclohexadiene, you get diastereo selectivity, not great yield, but it is productive for this case. Moving on to more interesting dienes, and so looking at a range of dienes plus this anophyl-ene or dienophile, we can get good, or more specifically, Susie Stevenson and the Eric Farrar lab can get good product yield as well as good diastereo selectivity with this earth-abundant chromium catalyst. Looking at the dienophile scope, again, very good diastereo selectivity, decent product yield observed for this without a auxiliary agent. We don't have to have the methyl viologen around to make the chemistry occur. Differential novel reactivity. Why would you want to do this if you can do it some other way? Well, if you can carry out chemistry, get good yield, good diastereo selectivity, better than you can with other chemistry, then it starts to become interesting. So how is this happening? The mechanism we think for how the reaction is occurring is the chromium is photoexcited. This excited state is a strong oxidant. It oxidizes the olefin. The radical cation of the olefin reacts with the diene, making this cycloaddition product. This type cycloaddition product can come back here and be reduced and reform the chromium site, the chromium species, which can then carry on. It could also come over here and do electron transfer to another olefin that doesn't have a metal involved, and a chain reaction. NMR experiments suggest that, in fact, it is dominantly this cycle where the chromium is being used catalytically. It's involved in every step. If you shine light on the reaction, stop. The reaction stops. Turn light back on. The reaction continues on towards product. And so it is a photocatalytic process. Computationally, we can compute the excited state, the correction for having multiple determinants. We talked about the fact that there was more than one description of where the electrons. On the excitation, that's worth 13. On the product side, it's also important. Without these effects, all of these observed reactions wouldn't happen, and so the model wouldn't be useful. So what have we, summarizing, we've seen product selectivity, energy reduction, reagent reduction, diastereo selectivity. We've answered the first question, yes, we can use a earth-abundant metal in photoredox catalysis. The long-lived excited state of chromium can be used to eliminate an auxiliary agent, and stereo control, or specifically di-stereo control, can be achieved, and we can get novel reactivity.
First of all, I'd like to thank the organizers for organizing the webinar. I'd also thank Tony for setting up the principles of grain chemistry in his talk. Today I'd like to talk about some work that we've done at the University of Kansas, in particular as part of the Center for Environmentally Beneficial Catalysis, which is a center headed by Dr. Bala Subramaniam there in the list of co-authors. And this particular project comes from a program from NSF EPA, jointly funded, called the Networks for Sustainable Material Synthesis or Materials Design and Synthesis, NSMDS. And our approach is to try and develop a protocol or a very highly interdisciplinary model for developing sustainable catalytic processes for the chemical industry. How do you come up with novel ways that are environmentally beneficial to produce the commodity chemicals that we rely on every day? So just to give you an overview of the interdisciplinary nature of this project, we can look at the project team to begin with. I'm here, I'm the PI of the grant, and my expertise is primarily in molecular modeling, computational material science, a lot of work on interfaces, calculating phase equilibria, et cetera. My colleague, Ward Thompson, also in the molecular scale modeling area, is an expert in chemical dynamics, some electronic structure theory, and also understanding how reactions take place in nanostructured materials. We then have, as part of this very highly interdisciplinary team, two members from the Department of Chemical Engineering, Bala Subramaniam, who is the director of the Center for Environmentally Beneficial Catalysis. His expertise is in reaction media, green catalysis in general, reaction engineering, and life cycle analysis, which I'll be talking about quite a bit. His colleague, R.V. Chowdhury, is an expert in multi-phase catalytic reactors, catalyst design, and reaction kinetics. And finally, we have John Tunge, who's an organic chemist, also working quite heavily in catalyst design and also understanding of reaction mechanisms. Now, one of the beauties of the CBC, the Center for Environmentally Beneficial Catalysis, is we have a really large cadre of people that help us do all the work. We have a number of postdoctoral associates who have been working on these projects, who've been coming in and out of this particular project. A few of us have left us. Krista just went to New Zealand to be closer to the beach, I think. And Jesse, my student, just graduated. But we have a large number of graduate students, undergrads, and some really fantastic professional staff that have really helped us get this going. And they span the expertise. We have people, Hansi, Krista, Jesse, Hiranya, in computational chemistry. The rest were primarily in either chemical engineering or organic synthesis. So it's really quite an interdisciplinary team. So our basic approach that we refer to as an integrated design approach essentially involves a large number of efforts on the experimental realm, from catalyst synthesis, trying to understand the kinetics and mechanisms of catalytic pathways, to the development of catalytic media, the support media for the system, to be both benign and tunable, and then also to really try and understand how you scale these up into chemical reactors. That is then combined with modeling that spans the scales from the molecular to the reactor scale. So we have quantum chemistry and molecular level simulation, and then more empirical kinetic modeling, trying to base on the reaction mechanisms, and then reactor simulation and life cycle assessment to try and understand the economics and environmental impact of all of the different systems. One of the main advantages to working with a group such as the CEBC is the strong interaction with industry. We have a very strong industrial advisory board. These are some of the companies that have been involved with us. We also have a very strong scientific advisory board, and they meet twice a year, and the students have to give their pitches on all of their projects to the board. And then, and then we get feedback from the companies. We also get buy-in from the companies, perhaps to spin off side projects or to get industrial funding. And so this interaction of the students and postdocs and the faculty with industry has really strengthened our understanding of what the challenges are in the chemical industry. And again, you know, emphasizing that we can really leverage a lot of the existing infrastructure at the CEBC. We have a large amount of R&D total. We've had 22 industrial partners that have been involved, 44 inventions, 12 patents, and then a large cadre of students and postdocs that have really been able to help us go forward. And again, this is the mission of the CEBC, essentially to invent cleaner, safer, energy-efficient technologies for commodity chemicals that protect the planet and human health. So I thought I would start off with an example of the type of grand challenge that in the chemical industry that we're interested in trying to solve. And one of the things I'll talk a bit about more as one part of the current project is the epoxidation of ethylene to ethylene oxide. Ethylene oxide is a commodity chemical. It's primarily a chemical intermediate. It's used as an intermediate to manufacture a large number of the types of things we have in the everyday world. I'll talk a bit about that later. But one of the problems is that it's the second largest emitter of CO2 in terms of commodity chemical production. And what that means is currently one of the standard routes of going from ethylene to ethylene oxide involves direct reaction of oxygen with ethylene in the gas phase using a silver catalyst at relatively high temperatures to form ethylene oxide. Because of the high temperatures, a substantial fraction, about 15% of the product, reactant and product, are burned off in the process, essentially converted to CO2. And so not only are you losing your feedstock, but you're also creating unwanted greenhouse gases. So the largest emitter is ammonia in this particular case. From an economic standpoint, you know, this is about a $2 million a year loss to industry. So that's an example of one particular sub-project. The overall project goal here is to apply this integrated design approach to grand challenges in the chemical industry. And we've picked, as part of this proposal, part of this project, two particular test beds. One is the non-phosgene CO2-based route to dimethyl carbonate, essentially starting with ethylene and then going further through multi-steps to dimethyl carbonate. Right now, the traditional approach to synthesizing dimethyl carbonate, which is a precursor for a lot of polycarbonate plastics, has phosgene as an intermediate. Again, phosgene is a very highly toxic chemical. The second approach is testbed B, is to design a less wasteful catalytic pathway from butadiene to adipic acid. Adipic acid is the precursor for nylon. So just to give a brief overview of both of these, and then I'll talk about one specific aspect. If we look at the non-phosgene route from ethylene to DMC, one of the reasons you want to start with a chemical like ethylene in this process is there's been a real change in the petroleum industry in terms of the emphasis now on a lot of shale oil products. And so you're looking at industry trying to find smaller carbon, looking at C2 and C3 carbons in order to things that you can get from shale gas in the system. And so ethylene is becoming a more important feedstock for the chemical industry. So the first part of this process involves the oxidation of ethylene to ethylene oxide. And this is the one that I'm going to talk about the most. I mean, the time limitations, I can't talk about every product in detail, but I'll be essentially focusing in on that particular step. Step 2 involves the carboxylation of the ethylene oxide to ethylene carbonate. And then finally, a transesterification of the ethylene carbonate using methanol to dimethyl carbonate. The test bed B here involves starting off with butadiene and trying to convert essentially to a dipaldehyde, which can then be easily converted to adipic acid, this precursor for nylon. The conventional process for this involves a starting material of cyclohexane and uses nitric acid and generates it generates NO2 as a waste product, but it also still generates a lot of residual nitric acid in the system. And so a clean this would be to actually look at a rhodium catalyzed hydroformylation of the butadiene. Unfortunately, there are two particular products for this. There's the pent-3-enal and there's the pent-4-enal. The pent-3-enal is favored, and so what we're trying to do is work on a process by which we can stop the procedure here before it can go on to the undesired products, perform an isomerization to go to the desired product. So there's a lot of work in terms of understanding the kinetic mechanisms that are going on here. So as a specific example, I'm going to spend a bit of time talking about the epoxidation of ethylene to ethylene oxide. Again, this is a $30 billion a year process. It's growing by about 5% each year. It's the 14th largest volume organic material, organic chemical that's being produced. And it's essential building block for a lot of materials. If you look at all of the particular consumer products over here, from antifreeze to fabrics to plastics, that it actually is used as an intermediate to produce a large number of chemicals. So we can look at it in terms of, here's a list of the 18 large volume chemicals. And if we look at greenhouse gas emission, we see, if you take out things like methanol and propylene, where basically the energy is coming essentially from the cracking process and not necessarily from the actual chemical formation, ammonia and ethylene oxide here are the two largest producers of greenhouse gases in terms of the commodity chemical production. So what we first started trying to do at the CBC was to develop an alternative technology to the original silver catalyzed system. And here we have we're looking at the epoxidation of ethylene. In the silver catalyzed system, oxygen is used as the oxidant. One of the problems there is you're working at relatively high temperatures. You've got mixtures of ethylene and oxygen in the system, and so you have severe safety concerns. One of the things we're trying to do in the CBC is lower those safety concerns by performing this in the liquid phase. And one aspect of the CBC that's been a major theme since its founding is the use of gas-expanded liquids. A gas-expanded liquid is when you have a high partial pressure of a particular gas above some organic liquid. And what you find is that in many cases that gas is highly soluble in the liquid, and so you can actually expand, by increasing the pressure of the gas, you can expand the volume of that system. And so here we're actually using ethylene expanded methanol. So we have ethylene in the methanol phase here, somewhat high pressures but relatively low temperatures. That's currently room temperature in Kansas. And to form the ethylene oxide. So again, this eliminates the CO2 emissions from this particular process. Here, a rhenium catalyst is being used in a homogeneous catalysis formulation. The major downside is this is a pretty expensive catalyst. Rhenium is not cheap here. And so we can do an analysis. The other downside is if we do an analysis of this using life cycle analysis, which is trying to understand both the economic impact and the environmental impact, we see that the total greenhouse gas emissions is not considerably better than the conventional process if you take into account what you need to do to form the hydrogen peroxide. So if you look at, from a cradle to grate, basically looking at what you need to actually form the raw materials. Now this can, we have a number of ways of trying to improve this so we can actually get that to be a lot better, but still, because of the expense of the catalyst, it's really not economically viable. So we really need to do better. So one of the most important things in the CBC's process, and in this process that we're going forward with, is the idea of doing life cycle analysis at all points of the spectrum. Basically, looking at the economic analysis, looking at the process itself, doing a full life cycle assessment. There are a number of programs that one can do this to help us inform what's going to be feasible. And we do this from the outset in order to keep us from wasting time with processes that would never be able to be scaled up. So we can be cost competitive with a number of these. By looking at a few things, for example, going to a mixed ethylene feedstock. If you don't have to actually separate ethylene and ethane from each other, you save a lot of energy. You basically use the process itself as a separation process of ethylene and ethylene. That'll save you about 10%. You can try and improve the efficiency of the peroxide and then look at working on a cheaper catalyst. If we do all of this, we can get to, we believe, a 25% reduction in the greenhouse gas emissions for this particular process. So our new process is a heterogeneous catalysis method in which we use the same ethylene expanded methanol, except we have silicon nanopores, metal doped silicon nanopores as the catalyst. So here we have a variety of different types of silicon nanopores as the supports. This also gives negligible CO2 as a byproduct. There are a number of possible products. The selectivity is extremely high towards ethylene oxide. We're trying to optimize that. There's some of the byproducts are ethylene glycol, which is not a bad byproduct to have. If you could actually develop a process from ethylene to ethylene glycol, you would be fine. The other one is not as useful. But here we involve a very highly connected synergy between the experimental and the computational groups. The experimentalists are responsible for a lot of the characterization here shown in some of these TEM images. They can really do a lot of reactor studies to understand how to maximize the productivity. They can do the life cycle analysis. My group, we're involved in a lot of molecular simulations to try and understand how do these particular solvent materials, liquid solvent materials behave when you get inside the pore. That's not that experimentally accessible. And then we can do electronic structure calculations to understand the reaction pathway. So there have been a number of studies. The first thing that they found is that actually using these mesoporous catalysts, we can get significant activity, but one problem that we have is that these tend to decompose the H2O2, the hydrogen peroxide. And you can look here, if you look at the H2O2 selectivity to product, you can see that basically only about 10% of the H2O2 is being used. This niobium TUD1 catalyst seems to work the best. There's also a problem with metal leaching, with the metal that's doped inside the catalyst, inside the pore to leach out into the system. One hypothesis that we have is that it's the catalyst acidity which is causing this. So we've done a number of studies for this. One is actually experimental. To decrease the acidity, one is to pre-treat with sodium bicarbonate. This actually caused the productivity to go way up, and it's to be comparable with the other CBC homogeneous process and the industrial silver process. We still have some issues with the decomposition of H2O2. You can also decrease the acidity by decreasing the metal loading. If you decrease the metal loading, you can you can get up to about 80% selectivity of hydrogen peroxide towards the products. And so the question is how do we sort of combine these? In this particular case, you actually have more problems with metal leaching. So this is where computational chemistry comes in. So we've done a number of studies. Here, this is an example starting with a fragment of niobial silicate, kind of a small-scale model of our system. We can map out the reaction pathway, starting from the system with the catalyst, absorption of the hydrogen peroxide, absorption of the ethylene. Here, there's a transition state, and then you end up with the product, which then you get deabsorption of water, and then you get deabsorption of the product, and then dehydration to form the original catalyst back. If you look at this, the uncatalyzed reaction, this transition state is about 25 kilocalories per mole. With the catalyst, it goes down to about 11.6 according to the calculations. And this is favorable relative to a TS1 catalyst, which is about 16.7. So here we can map out this pathway pretty rigorously. We can also look at the effective acid sites. So by looking at niobium hydroxide here, we can see what happens when we add hydrogen peroxide to this. One finds that it actually does end up with two problems. You get H2O decomposition from this acid site, and you also end up with the breaking of this NBO bond to get metal leaching into the liquid phase. If you pre-treat this, essentially replacing this hydrogen with the sodium, you actually inhibit this particular pathway for the decomposition. So some future work for this particular aspect of the project is one thing that we're trying right now is to use methanol as the solvent for H2O2. Right now, currently, it's typically in water. And then also explore a number of other coordination motifs for the niobium catalyst. Within the modeling is to actually try and model this idea of increasing the niobium loading by actually adding in niobium sites here to understand how increasing the amount of niobium in the system will affect the metal leaching. Modeling the baseline, which just look at the silicon nanopore itself without any metal loading, and then also look at the effect of different transition metals in the system. We can also work to increase the structural complexity by adding more to this fragment and using more advanced quantum mechanical, molecular mechanics combined methods. One aspect that I've been involved in my group is to try and look at the solvent media itself. So here, as an example, we have phase equilibrium that we've calculated using Monte Carlo simulation. So this is for a ethylene methanol mixture. And we see here the gas phase is primarily ethylene. We can get up to a 30% mole fraction of ethylene in the liquid phase. These predictions here, this has been experimentally done. And so our models are actually fitting the experiment very well, much better than sort of standard Ping-Robinson modeling you get in usual chemical engineering programs. We can also look at the transport properties, and you can see you can tune the transport of ethylene in this liquid phase quite dramatically simply by increasing the pressure. As you go up to 55 bar, you've essentially increased the diffusion constant by over a factor of 2 of ethylene inside the system. We can also look at what happens when you start adding water. We can look at the solubility of ethylene in the system. These are often things which these Ping-Robinson type equations of state models don't often do too well. But more importantly, and I'm going to have a movie here to start, more importantly, we can actually model the reactant mixture inside the pore. And one of the things that we found here is that the pore composition, the pore surface composition, can modulate the ethylene composition quite dramatically. If you look at the pore, you can functionalize these silica pores with OH groups to get hydrophilic sites, or you can have them more terminated with hydrogens or methyl groups to get hydrophobic sites. And if we go from a hydrophilic site to a hydrophobic site, we can see, for For example, these black symbols are the calculations you get in the bulk for the ethylene composition. If you have a hydrophilic pore, one sees that you don't get a big change in the composition of the ethylene, of this mixture from the bulk. However, for a hydrophobic pore, you get a significant enhancement of the ethylene composition inside the pore. These are quantities that are very, very difficult for experimentalists to probe, and so the simulations provide us with a lot of phenomenology. We can also get towards the full system by looking at a full 5-component mixture. And this is a case of looking at some MD simulations on the pore bulk systems. And what you actually see, this is a mixture of ethylene and methanol. This is at this 40 bar pressure for the hydrophilic pore. And we can get a good picture of what's going on inside the pore on a very detailed molecular level to help the reaction engineers understand how to create models for this. So that's a bit about the science. I want to talk just about another minute or so about some of the outreach that we're doing. As part of this project, the project is paying for 2 undergraduates to work with our NSF Research Experience for Teachers program that we have at the CEBC. And so we had 2 undergraduates, one of them, Tom here, was able to design a module and work with the teachers to design a module for actually illustrating entropy using an Ising model, coin flip type of procedure. This year, we have 2 undergraduates working with Dr. Subramaniam to try and introduce modules for life cycle analysis, or examples, real life examples from the CBC for life cycle analysis into the junior level chemical engineering curriculum. And finally, we've also been working, the chemistry department has a carnival of chemistry every year, and the people from this particular project have actually been working and implementing activities for green chemistry within our Carnival of Chemistry to basically show how green chemistry and engineering can reduce the environmental impact of chemical manufacturing, but in a relatively fun way. So just some brief concluding remarks. Emerging feedstocks from shale gas basically provide exciting challenges for developing novel technologies. These are really potential game changers for the US industry. The multi-scale approach that we've developed really benefits from a large number of faculty members with differing expertise. Finally, one of the most important aspects of this is to integrate life cycle analysis, especially with regard to looking at sustainability, directly into the process of development so that you can make sure that you're going toward a goal which will be both sustainable and feasible economically. So finally, thank you. And I guess the parting remark I want to leave is that don't be afraid of interdisciplinarity. It's a really fun thing to do. A lot of the stuff that we're doing now is something that I wouldn't have dreamed up on my own, and only because we brought together this particular team of experts towards this common goal that we were able to actually, I think, be better than as a group than each one of us individually.
I'd like to begin our questions. First question for Professor Rappé, which is, so we've heard a lot about chromium here. Chromium we know has got some big advantages, as you've discussed. What about iron?
We would certainly love to use iron, and certainly iron is our aspirational goal. Iron it would be great, but it's really substantially more difficult in terms of experimentally to study and as well as computationally to study iron. Iron, the excited states aren't in the right place. It's a great spin crossover system in that the excited state is low in energy, but if you're trying to capture energy in the excited states, that's not so good. And so it's a big challenge to do iron. We hope that we can learn enough from these preliminary studies on chromium to be able to figure out what kind of ligand combination one would have to be able to use iron. Iron would be absolutely wonderful. Matt Law at Irvine reported a couple years ago in JAX that 10% of the iron pyrite that is in mine waste would be adequate for providing the U.S. energy needs if you could make a 10% efficient catalyst. So turning the material that's cheaper than dirt into a productive catalyst would be absolutely wonderful, and that's certainly an aspirational goal.
So now a question for Professor Laird. Brian, homogeneous, heterogeneous catalysis. You discussed heterogeneous catalysis. Why heterogeneous?
So the original process that the CBC had developed using the rhenium catalyst was a homogeneous system. The one we're moving to now is a heterogeneous catalysis approach. One of the advantages, or the advantages to heterogeneous catalysis is, first of all, you don't have to worry about catalyst solubility, which is a big thing to not have to worry about. You also don't have to worry about separating the catalyst from your final products because the separations are fairly easily, they're done physically. That being said, we actually are still exploring both avenues. As I mentioned in the talk, we are looking at other niobium coordination motifs, and some of those involve looking at homogeneous catalysis. So a lot of it just boils down to what the life cycle analysis tells us when we look at this, and we have to take into account issues of things like separating the catalysts into account. And so all of that's taken into account. So in a sense, we're not wedded to one or the other. Whichever one is most convenient, whichever one will lead us to our goal is the one we're going to use.
Well, very good. Let me follow that up with another question for you, Brian. Tell us a little bit about the Center for Environmentally Beneficial Catalysis. How was this inception? How's it evolved?
Yeah, this particular center has been around about 15 years. It started around 2000, basically developed from a collaboration that had been that had come about between Bala Subramaniam in the chemical engineering department and Daryl Bush in our department, who's the former ACS president. And one of the technologies that they had been looking at significantly were these gas expanded liquids, more specifically carbon dioxide expanded liquids, where you can perform catalysis by actually changing the reaction media to by dissolving huge amounts of CO2, or in our case here ethylene, into the liquid phase. You end up with a sort of a novel type of liquid that is highly tunable in terms of its transport properties. It's often more favorable in terms of catalyst solubility. And so there's a number of things that you can do with that. You can also, because of this, because you increase the volume with this, let's say CO2 in that particular case, you end up with being able to use a relatively small amount of your organic solvent to generate a much larger amount of solvent volume in the system. And so there was this collaboration between Dr. Subramaniam and Dr. Bush. I got involved because I do a lot of liquid state theory, understanding phase transitions. And so this idea of the gas expanded liquids intrigued me because it was just a very novel phase of matter. And so we got involved doing a number of different simulations. And as part of all these collaborations, we realized there were a lot of people starting to get together, inorganic chemists, chemical engineers. And so we applied for a center to the original NSF program, the Energy Research Centers, the ERCs, and the center was founded on the basis of that successful grant. But we've since graduated from that initial NSF model to something that's been more sustainable. A lot of the emphasis on that original CBC grant was in terms of getting industrial partners. You had to really show that you had a strong industrial partnership for that. To build the center. And so since then, we've gotten a number of collaborative grants basically from Department of Energy, from a number of industrial sources, ADM, et cetera. And so it's really become quite a self-sustaining center.
Well, one thing that's staggering about both of the centers that you operate with is the amount of industrial collaboration that you have. And I think that it speaks really well for the impact that you're having on sustainability as a whole. Now, Tony, within all of this, there's an awfully complicated series of things going on here. How is it, I mean, this is one of the other questions from the audience, how do you actually define substoichiometric with respect to the catalysts in these reactions?
Well, what I mean by substoichiometric is that, for example, on a molar basis, the catalyst is there, say at 5% relative to a reagent being there at 100%. And so it's just, you're not using your, say, chromium complex in a stoichiometric amount, equivalent amount to the reagents you're interested in. So it's just there in a small but useful amount that gets turned over repeatedly during the course of the reaction.
So, Brian, I have a question for you from the audience. It's exactly how brilliantly can you design these now? So can you create pores that can reactivate a catalyst or that can inactivate a reaction toxin in your systems?
I mean, from these types of silicon nanopores, it's somewhat rather difficult to actually control the specific function. I mean, control the specific surface chemistry, because you don't have a lot of characterization of, you know, once you've created something, exactly what does it look like inside the pore. That's actually fairly hard to do. And so, you know, you can do various things to try and increase, for example, its hydrophobicity or its hydrophilicity. And we can explore those within molecular modeling in terms of looking at very generic models and how those various aspects affect the system that we're looking at. You can change functionality by changing the type of metal you're doping into the system. And so that, for example, in terms of inactivating toxins, which was one of the parts of the questions here, you can try and work to optimize that towards a particular deactivation mechanism for that particular toxin. And so you do have a fair amount of freedom, but it's, in terms of the silicon nanopores, it's tough. Now you can get more into things like MOFs, metal organic frameworks, and these are a lot easier to tune because you can do crystal structures and figure out exactly what it is that you have. And then it becomes a lot easier from a calculation standpoint, because often it's hard for us to do calculations, you know, build the model of the system for the computer if we don't know what the model of the system is to begin with.
Well, there's a related question that's coming in from the audience. So specifically in one of the reactions you've discussed, how is it that bicarbonate is being used to activate the pores?
Well, actually, the bicarbonate actually doesn't, it doesn't necessarily deactivate the pores relative to the catalytic effect. What it does is it shuts down one of the major mechanisms for the decomposition of the oxidant, the H2O2. And because, you know, if it decomposes, it forms water, which is useless for us in that system. And so the idea, as I showed in the slides, one of the things we've seen in the computational chemistry analysis is that if you replace the hydrogen, you know, if you have an OH group, a Bronsted acid site in your system, that if you replace that with the sodium, that shuts down that mechanism of decomposition.
Okay. And another question from the audience. Tony, can you tell us a little more about the importance of green chemistry as you actually begin with first the structure of what you want to accomplish in a reaction, and then arriving at an early process and then a scale up towards commercialization?
Well, I would say there's several parts in terms of answering that. One, we're really in the business of training students, okay, graduate students, undergraduates, postdocs, and going through issues associated with green chemistry, even if you're just developing a catalyst, is certainly important. Another take on that would be if you chose to carry out chemistry that in your, say, initial drug screening, if you chose to use chemistry that prevented or eliminated the possibility of making that one key molecule that's going to actually help anti-cancer, that would be tragic. And so there's a balance between, drug discovery, you want to discover the drug. As you scale up, you have the drug. It's a different game. But I think as time moves on in like photocatalyst research, as you open up new reaction pathways, differential, making products that haven't been made before, could expand the discovery process.
Well, there's a question that's related to that that's coming in, but I'm actually going to twist it a little bit. So the question, and I'll ask both of you. So Tony, the question for you then will be, so how can this research be made applicable for drug discovery and drug development in developing nations, developing economies, the rest of the world that's not so industrialized? But please let me, before you answer, I'm going to ask the same question,
Yes, sure.
but with respect to Brian, I think that we change this question a little bit.
Okay.
How do you do this looking at industrial processes for commodities production, which can perhaps be even more important in emerging economies? And so then back to you, Tony.
I would say that cost, simplicity, if you will, principles associated with green chemistry of reagent reduction, auxiliary reduction, the more straightforward you can make the process, the more generally useful it can be. And using iron instead of ruthenium, cost comes in and plays a big role. And so I think that keeping in mind that, if you will, in this Human Development Index, a big part of our goal is moving the developing world up in terms of health and well-being.
I think, with regard to industry, the answers are pretty much the same. The idea is, by looking carefully at these life cycle analysis and including the environmental impact, you're still working to try and reduce the cost. You're still trying to make it simpler in terms of being much more atom economical. And so I don't necessarily see a conflict between using using a green chemistry approach and this type of integrated design that we have in terms of looking at developing countries as well. Computational chemistry is cheap, usually. So we can do things
Brian,
cheaply.
Okay, another question for you. So how is it that you go about prioritizing the issues you want to address, the most toxic reactions, the industries, the products, and how do you work backwards to work on the highest priority problems first?
That's a really good question. I mean, one of the things, if you look from my talk, we focused on this ethylene oxide just because in terms of greenhouse gas emissions, it's actually the second largest one. So, we are looking at a problem sort of initially that is quite high impact. Now, the question, I believe, is looking at, is there sort of a systematic way we can start doing this? And I think that's a very good question. A lot of what we've been doing has been sort of looking at these more on a one-off approach, looking at the various types of processes that are out there and thinking about what we can improve. One of the things that we do plan on looking is trying to be more proactive in looking at toxicity. And so Tony and I were both at a meeting earlier with the PIs where the EPA was there, and they were talking a lot about all of their new software and projects for really helping people understand the toxicity of the various parts and include toxicity in these types of analyses. And so I think right now it's less of a systematic approach, but we're moving towards that.
Okay. Now, using computational chemistry, are there rules that dictate which types of metallic catalysis are going to work in these types of reactions, Tony?
I would say part of what we're trying to do is figure those out. We're at a fairly early stage. I mean, I think clearly lifetime is important. The excited state has to be around long enough to be able to carry out the chemistry. That's an important factor. Has to be of the right energy, the excited state. If it's too high, you're not going to use visible light. If it's too low, it's not going to deliver enough energy. And so trying to get that right balance. Initially, we thought that chromophore was really important, that these had to be really, really bright. Turns out that's not really the case. That's not the dominant factor. That if the catalyst, if photocatalyst is too bright, you actually, it absorbs all the photons really early in the path, and you don't get efficient excitation of the whole solution. And so there's a balance there in terms of what to do. But I would say we are definitely early on. I mean, if we were further along, we would be talking about iron.
Okay. So, Brian, now a question for you again from the audience. Now, how could you use computational chemistry to predict what's going to happen to and the question is a drug, but I won't even restrict the question to that, but a general molecule, what's going to happen to it over time in a solvent, and particularly something such as water?
That's a very good question. I think one of the things we look at a lot is trying to understand degradation pathways. And so, generally the approach is you see that there's something that's a problem. For example, here in our case, we had the decomposition of the H2O2. The experimentalists think of some ways which might work. If we can then use the computational chemistry to understand exactly what those reaction pathways are, we can actually map out the energetics of that to figure out what the mechanism is. Once you understand the mechanism, you can then try and work to figure out how you work to ameliorate that. An example in this case is essentially adding in the sodium bicarbonate dramatically decreased the amount of hydrogen peroxide decomposition. One of the things that the computational chemistry informed us of is that if we use methanol as the solvent, we should be able to inhibit that decomposition even more. So generally, the question sort of asks, how does computational chemistry do to predict things? I don't necessarily think that that's the approach we always use. The approach we always use is really a back and forth, a very interactive team of the experimentalists and the computational chemists. Basically, the experimentalists helping us understand what the problems are. We can do the calculations, figure out what the mechanisms are. So it's really a back and forth. I think just doing pure computational chemistry in a vacuum really won't get you anywhere. But neither will just doing experiments in a vacuum.
Yes. Tony, a question for you. How about evaluating the potential toxicity of chromium complexes?
So chromium, we certainly get asked this a lot. Chromium-3, the oxidation state of chromium that's used in this photocatalyst and used fairly commonly in organometallic chemistry, really doesn't have a significant toxicity. Chromium-6, the Aaron Blakovich movie issue, Chromium-6 definitely has severe toxicity issues of a wide range. And so if you look at measures of toxicity for chromium, they're really all over the map in terms of how you value or evaluate particular parts. The bottom line would be we really want to use iron, but we don't know how to, and we're trying to learn using chromium. The biggest problem with using chromium in terms of chromium-3 is you certainly don't want to combust the waste product. You don't want to convert it into chromium-6. You want to keep it in a lower oxidation state, which is straightforward. You can go to your neighborhood vitamin store and buy a big bottle of a chromium-3 complex and take it as a dietary aid. You just don't want to get to chromium-6. Now, perception, if you will, is reality, and chromium-6 is a problem. I think it can be used certainly safely. Chromium-3 can be used safely in the lab, and a lot of knowledge can be gained from it.
I have one other question for you, Tony. So you've already mentioned to us that you consider a lot of your work as after the drug candidate has been selected, but what about playbacks? So the new chemistry that you've been developing, are there beneficial aspects that play back into drug discovery?
I mean, we're early on in the sense of we haven't really gotten that far. But I would say that the big selling point would be novel chemistry, carrying out transformations that, shall we say, can't be done now, particularly, say, saturated, primary, secondary CH bonds. Being able to do that inexpensively and quickly is a real primary goal for us.
Now, Brian, you've shown us some brilliant chemistry, but discuss for us some of the pros and cons of using niobium as a catalyst.
So, I guess I'll start by looking at some of the advantages. That it's certainly much cheaper than either silver or rhenium that were used in some of the other systems. As far as I know, it doesn't have very high toxicity. I'm not an expert in toxicity. We have other people for that to help us understand that, and they've told us that this particular process should be fine. For us, really looking at the niobium is more a question of can we develop something that has a high activity, and so we're not wedded to niobium. We're also looking at tungsten as another example, but certainly using something like niobium relative to a lot of the more expensive metals is a significant advantage.
We only have time for one more question, so I'm directing this to Tony. Could you tell us a little more in detail about the computational methods that you use?
So what I've talked about today is predominantly electronic structure-based techniques, and we use dominantly a density functional approach that uses the APFD functional. These things tend to take names of the authors of the paper. We selected the APFD functional because of its outstanding treatment of dispersion. And so interactions with drug molecules, pi-pi interactions, really important to get that right. And so we use the APFD functional, time-dependent density functional theory to calculate excited states, and then this MD or multi-determinantal DFT, where we include more than one determinant in the picture, is critical for looking at these high-spin type complexes.
Well, gentlemen, thank you very much. And what we've got time left to do now is to ask each of you in turn for some final thoughts about what you'd really like to leave with the audience as the most important points of your presentations.
I think I would just like to reiterate what I said sort of towards the end of my talk, that I really think that people shouldn't be afraid of working in an interdisciplinary environment. I'm trained mostly as a classical statistical mechanician. Most of my work was on very simple things like Leonard-Jones, hard spheres, looking at really basic liquid state physics. And I started getting interested in the types of liquid phases that they were looking at. And so we really, this is something that I would have never done if it weren't for my interactions with chemical engineers, organic chemists, and even other quantum chemists. And so oftentimes in science, we have the problem, especially in academia, where collaboration is not necessarily hardwired into the way you're rewarded, especially in your early years. And I really think it's important, especially these days, that you try and seek out people that have a very different expertise than yours, because you can generally figure out something really cool to do.
We'd love to see you here at the conference next year if you can make it. It'll be June 14th through 16th, 2016. And certainly we thank both of our speakers for not only great discussion, but some really dynamic presentations. And audience, thank you once again, both for tuning in and for all your questions.
Thank you for watching this presentation. ACS Webinars is provided as a service of the American Chemical Society as your chemistry source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.